Hola, hola.
¿Puedes mandar una foto del número serial?
Hola, hola. ¿Se oye bien fuerte? Hola, hola. Ahora sí. Hola, hola.
Sí, mandé las. ¿Sí? Y luego la semana pasada estábamos en.
Ahí está, habla.
Gracias.
Sí,
Sí funciona.
Con nativo fue. Voy a ver. Ahorita empezamos. ¿Alguien más? La costumbre. Ahorita empezamos. Están cambiando las pilas. Micrófonos. Y en lo que a ver si viene el script. Ya está chido. Va, ¿no?
Gracias.
Entonces, más o menos 25 minutos para ver si hay preguntas. Pero bueno, pueden preguntar también a cualquier momento.
Hola, hola. Hola, hola. Hola.
Perfecto. Muchas gracias. ¿Ya está transmitiendo? Perfecto. Sí, vi.
Entonces ya tú lo puedes sacar a alguien, meter a alguien, o puedes incluso.
Ok.
Lo que sea.
Ok. Perfecto. ¿Vale? Gracias. Pues yo creo que empezamos para que sea a las 30. ¿No? Okay, let's start. Thank you very much for joining in person. It's very important. Also in Zoom, we have some people. So, okay, we have today the special colloquium, and we will have two talks. The first one is simulating the multi-scale environment of supermassive black holes by Dr. Hector Olivares, who is a postdoc at Aveiro University. He is from Mexico, of course, from Ciudad, and he did his PhD in Frankfurt at Goethe University. Please, Hector.
Thank you, Alejandro. So I will start my talk by talking a bit about the Event Horizon Telescope. So the Event Horizon Telescope, or DHT, is a network of radio telescopes that is scattered around the globe, and that when it points to some source, it is able to obtain images at a very high resolution using a technique called very long baseline interferometry. It is a very large collaboration with more than 300 members in more than 6 institutions around the world. several of them are here at the UNAM. And in fact, Mexico and Latin America play both an important role. Some of the, some crucial stations are located in these countries. We have the LMT here nearby in Puebla, and also we have the ALMA and APEX telescopes in Chile. So the amazing resolution power of this instrument has been used to obtain the first images of the shadows of black holes. You can see them here. These are the shadows of Sagittarius A star, the black hole at the center of our galaxy, and also of the black hole at the center of the galaxy M87. These were released in big press events. You can see there the press conference in Puebla, in Brussels, and also the one in Mexico City here. This data that has been released corresponds only to the observing campaign of 2017, but there have been more observing campaigns after that, and there are also other targets. So there is still a lot of science to be done. Okay. So these images may look blurry, but actually there is a lot that we have already learned from them. We know that both of the black holes that have been observed are probably rotating. We know that magnetic fields are dynamically important close to the event horizon. And we also have gained some information on the electron thermodynamics. But probably the most remarkable aspect is that the shadows of the two black holes are both consistent with what we expect from the Kerr geometry. And this is probably one of the most amazing confirmations of the predictions of general relativity, as it spans 3 orders of magnitude in mass. But how are we able to obtain this information? This will be mainly the focus of my talk. I will talk a bit about how we gain information to be able to say these statements. So basically the model testing process in the EHT collaboration. I will also mention briefly its limitations, and will also try to explain on one idea that describes one direction that we could take to improve things. So the process of model testing is basically the following. We create a model of the system that we are observing. In this case, each of these 2 black holes. And in this model, we put all the physics that we want to test. Then we create synthetic observations and compare these synthetic observations with the actual observations obtained from the array. The process of building synthetic observations is a process that consists of several layers. So at the bottom, we could say that we have the spacetime. This is the scenario on which everything else happens. And at this stage, we can set properties, for example, the spin of the black hole. On top of this, we have our second layer, that is the behavior of plasma. On top of this, we make a simulation on how radiation behaves when crossing this plasma. And this will be the radiation that we will observe. So with the output of this, we go to the last stage, which is to take into account all the uncertainties from the instruments and the observing conditions. The reason why we can do this process at different independent steps is that the physical scales that corresponds to the processes involved are very different, and this allow us to decouple them. For example, the plasmas that orbit that surround the black hole are very dilute, and as a result, the disk mass is much smaller than the mass of the black hole. This allows us to decouple the evolution of plasma from the evolution of spacetime, because we expect no back reaction onto the spacetime. In a similar way, the cooling timescale is much larger compared to the inflow time of the plasma, and this allows us to decouple radiation from plasma dynamics. Yes?
When you include radiation in your accretion disk, that's going to cool off the disk, meaning that you are going to change the accretion rate. Why this is what you can do I mean, I know that we all do with decouple plasma from radiation, but do you think that is really a good thing that we are decoupling plasma from radiation? Because what I'm asking is
How bad is the approximation? No?
If you include self-consistent radiation self-consistently, then I think the accretion rate is going to change.
Right.
Which would mean that it's going to change a lot of physics.
Yes, that is true. So, well, in the general case, from the black hole systems that we know in the universe, not for all of them it is possible to do this decoupling. So, but precisely for the two targets that the EHT has observed, so M87 and Sagittarius A*, this decoupling is possible. So this is something that we can know from looking at the spectrum. So this kind of systems, Sagittarius A* and M87 have a spectrum that fits with what we call a radiatively inefficient accretion flow. So the name radiatively inefficient tell us that there is radiation doesn't play really, or cooling doesn't play really a very important role. But for other other systems like quasars or X-ray binaries, then this decoupling is not possible. So right. So I would like to just briefly say in a bit more detail about the two intermediate steps. So one is plasma dynamics. So this is the first layer after the space-time description. So the plasmas that surround the black hole are generally well described by the equations of ideal magnetohydrodynamics. And these are basically a set of conservation equations. Here they are written in covariant index notation, but they are basically the conservation of particle number, the conservation of energy and momentum, and the two Maxwell equations. So since they are basically conservation equations, in order to make these simulations, we use a particular kind of methods that are called finite volume methods. And these methods work basically in this way. We divide the simulation domain into a lot of several control volumes that can be also called computational cells. And each of these control volumes has some amount of a quantity that is supposed to be conserved, let's say particle number or energy or momentum. Then we use a set of closure relations in order to compute the fluxes of these conserved quantities at the boundaries of the control volumes. In this way, after one evolution step, everything that has gone outside these cells has entered the other cells. And this is part of the beauty of these methods, because in this way, every quantity that should be conserved is conserved to machine precision from one step to the other. Besides this, these methods are also very nice for resolving shock, and there are also part of a class of methods that are called high-resolution shock capturing schemes. I will take the occasion to make a small advertisement about one of such codes. This is the black hole accretion code. It's a code that I helped developing during my PhD, and of which I am still one of the main maintainers. This code was used for the Event Horizon Telescope Simulation Library, and it is freely available on this website. So we try to also to keep it well documented with manuals and tutorials. So if you are interested, you can download it and start making your own simulations. Let's go now to the next layer in the construction of the synthetic observations, and this is the description for the behavior of radiation. So the radiative transfer part. At this stage, we are no longer solving partial differential equations, but we are now solving ordinary differential equations, and there are two of them that describe that are used at this stage. The first one is the geodesic equation. The geodesic equation allows us to find the path of light rays in the curved spacetime. The other equation is the radiative transfer equation. This equation tells us, the amount of photons that are collected by these light rays while they cross the plasma. The ingredients that appear in these equations are this emissivity coefficient that tell us how much photons the plasma emits, some absorptivity coefficients that tell us how much it absorbs, as well as some rotation coefficients that tell us about which polarization modes are converted into which others. And in order to find these coefficients, one needs to understand the radiative processes that take place here. And in this situation, these are mainly synchrotron radiation, Bremsstrahlung, Compton, and Ampere production. However, at the frequencies at which the Event Horizon Telescope observes, the effect that is dominant is synchrotron radiation. So now that we have these ingredients, we can start creating our library of simulations. The HT simulation library is very large, but it consists mainly on a class of models that are called fiducial models. And these are built in this way. One constructs a torus of plasma in hydrodynamic equilibrium around the black hole. One adds some colloidal magnetic field and perturbs it. After some time, we let turbulence grow in the torus, and we end with a state that looks like the ones that are depicted here. You can see that the final state is turbulent, but it still has some. Well, it still preserves the original axisymmetry to some extent, and I would like you to remember this the fact that these simulations still show this symmetry. So there are one can vary several things in these models. One of these is, for example, the amount of magnetic flux. There are some models for which the magnetic field is more dynamically important than in others. And this gives rise to two different categories of models. For math models, the magnetic flux, the magnetic field plays a more important role. And it arrives even sometimes to completely stop accretion. This results in some powerful eruptions of magnetic flux, and it is also the models that produce the most powerful jets. And on the other hand, there are the same models. MAT stars for magnetically rested disk, and same for standard and normal evolution. These kind of models, in contrast, are turbulent but are quieter. They are like a stream like a quiet stream of water. So this is one of the things that one can vary, but there are other quantities that we can also explore their parameter space, like the black hole spin or some prescriptions for the electron thermodynamics. So now that we have the library of models, we need to define some observables that we will use to judge whether these models pass or fail. In the case of Sagittarius A star, there were, for example, 11 constraints that are things as for example, the size of the image at the observing frequency of the HT, or the total flux measured at some other frequencies. The plot that is shown here, it's a bit of a complex plot, but it contains all the models that were tested from the fiducial set. And the important thing to know is that only those models that are of plain green color, this one and this one, are those that pass all the constraints that are considered here, which are all of these except those based on variability. And this is very interesting because it already tells us about the large constraining power of the array. However, every time that one compares reality to a set of models, one needs to be aware that the conclusions that one extracts are valid only under the assumption that the reality, that the truth is contained within the universe of models. And in this respect, one needs to take into account something very important, that is that in order to keep tractable the problem of model explorations, some choices needed to be made. For example, in the fiducial model set, for all the models, the spin of the black hole is either parallel or anti-parallel to the angular momentum of the accretion disk. So this already poses one limitation, because we will not be able to find within the universe of models a case where these two quantities are not aligned, which could very well happen in nature. But there is even one thing that is a bit more worrying. In the plot in the previous slide, I showed you the models evaluated by all the constraints except the constraints on variability. Why is this? Well, this is because if one includes the constraint based on variability, then no model passes all the constraints any longer. So taking into comparability, there is no model that fits all the constraints. This is one big point of discussion in the collaboration even now, and there are several ideas that can be considered. Could it be, for example, that the variability constraint is too strict, or maybe there is some non-ideal physics or some extra ingredient that we are missing in our simulations? So, well, this certainly points just to one thing, and this is the need for improved theoretical models. Actually, well, the idea to expand the models that are used beyond the fiducial set is something that it is currently already done in the collaboration. In fact, there is a smaller set of models within the library that are called the exploratory models that consider some directions outside the fiducial set. And we have here, for example, the tilted models, which are those in which the spin and angular momentum of the accretion flow are not aligned. There are also models that consider non-thermal particle distribution functions for the electrons. There are also other directions that have been tried, for example, non-ideal effects that come from kinetic physics. And well, the idea behind this is that one could have non-ideal effects that result in some dissipation, and this may well make smoother the light curves, therefore decreasing the variability and maybe making models be more consistent with the variability constraints. Because the problem is precisely that the observed variability is much less than the simulated variability. However, there is one well set of models or one direction to explore that seems particularly interesting to me, and this is the models that consider information from the larger scales. There have been some works that make simulations of the accretion flow on the Sagittarius A star, taking into account very, very, very large scales. These scales are so large that the simulation boxes contain the Wolf-Rayet stars that are orbiting the black hole and that are thought to be the main contributors to the accretion flow. And actually, when one follows the stellar winds from the place where they are launched onto the black hole, one can find very interesting well, behaviors. In particular, the scenario that we find is something, well, that people find using these simulations is something that differs significantly from what we are used to in the fiducial simulations. So remember, for example, the symmetry that I mentioned, the residual axis symmetry from the fiducial simulations. So, well, it is no longer here. These plots are cuts of the simulation on the meridional plane. And you can see that one side of the disk is thick, the other side of the disk is thin, and even there is no well, there are some times in which the flux from the thin side is interrupted. So in addition to this, the magnetorotational instability, which is the main turbulent mechanism that is thought to drive accretion, in our simulations, seems to be relatively unimportant in this case. So it is to some extent suppressed, and actually the flow doesn't have enough time to circularize. It has very low angular momentum, and well, what this means is just that the since the turbulent angular momentum transport is suppressed, it basically sometimes reaches the black hole just because the stars launch it directly towards the black hole, and it is in this circumstance that it is accreted. However, well, it is also worth mentioning that this is not the only problem of the fiducial simulations that are currently used. There is another issue that is a bit interesting, which is the following. All of these simulations start by placing the torus around the black hole. This torus has a finite amount of mass, and the simulations never replenish this mass by any means. What this means is that eventually, well, most of the matter will be swallowed by the black hole, and the simulation will run out of mass. This produce, if one looks at the some time series of the extracted from the simulation, this manifests as a secular decreasing trend that can be problematic if one wants to study long-term variability. And by long-term, I don't mean years or scale of this. For Sagittarius A star, long-term is just a scale of hours. So this is relevant within well, an observation campaign of the Event Horizon Telescope. And so, well, I wanted to talk to you now about a work that I am currently doing with Monika Moshibrodska and Oliver Port, which has the goal of creating new simulation setups that try to address these limitations. So we want to create simulation setups that have a clearer connection to the physics at larger scales, that are controlled by a small number of parameters, and that are also of a computational cost comparable to that of the simulations that are already in the library. So this is the setup that we have proposed. So it is a relatively small setup. So we are not including the Wolf-Rayet stars or anything like this. It is comparable to that of the EHT simulations of the fiducial set, with a boundary of at 1,000 gravitational radii. And we fill this domain with matter following a transonic semi-analytic solution. So transonic just means that it transits from subsonic to supersonic at some sonic radius. And well, in addition to this, we inject some velocity perturbations at the boundary of the simulation with some prescribed spectrum. We then have only 5 parameters that we can control, which are the spin of the black hole, the sonic radius, the adiabatic index of the gas, the angular momentum, and the amplitude of the perturbations. This plot here, sorry, this table here shows some of the different parameters that we have explored. So let's see how this looks. Let's press play on the simulation. So this looks like this. The top panel is a cut on the equatorial plane of the domain. The bottom panels represent cuts on the meridional plane, and the first column is large scales, middle scales, and event horizon scales. We already see a difference with respect to the usual set of simulations, which is that normally all of the regions far away from the black hole are filled just with a tenuous artificial atmosphere. And in contrast, here we have some structures forming organically. We can see the formations of some filaments here. If we look at the middle and horizon scales, we can see that also we have the organic formation of a structure that resembles a torus. So, however, well, if one looks more in detail, it's a torus that it is not quite like the tora in the fiducial simulations. These torus are made of matter that is unbound. So it has enough, it doesn't escape because it is continually pressed by falling matter, but it has enough energy to fly away, which is different from what one typically has in the torus that start from hydrodynamic equilibrium. So we can then explore the parameter space and see that this simulation set, despite being simple, shows a phenomenology that is actually very rich. From here to here, we are increasing the angular momentum. And from here to here, we are increasing the perturbation amplitude. When we increase the angular, we can see that for low angular momentum and small perturbation amplitudes, we have accretion flows that are very smooth and quasi-spherical, similar to the well-known bond dissolution. If we move to the side at which we are increasing the angular momentum, we start seeing some axisymmetric structures more similar to what we are used to from the usual simulations. And if we go in the direction of increasing the perturbation amplitude, we find some more chaotic accretion patterns that are dominated by shocks and filaments. And of course, we have also combinations of the two. It is also interesting to notice that, depending on the perturbation amplitude, one can describe these models by existing analytic models. So, for instance, one can see that in this plot, for the case that has the larger perturbations, the temperature profile transitions from the isentropic curve to a slope that is more consistent with a model known as advection-dominated accretion flow. So, the phenomenology is very interesting. And now I want to show you the last plot. Yes. So this plot here shows the time series of the accretion rate for our models. All of the colored models are our own, the models built in this way. And for comparison, I have included here this black line that represents the same time series, but for a simulation from the EHT library. In particular, this is a sane simulation with zero spin. And the first thing that one can see is precisely the decreasing trend that I was mentioning. Here, the accretion rate starts high, but as the torus start running out of mass, we see this exponential increase until here that is, it is very small compared to what it was originally. By the way, this full time series corresponds of something like 11 hours or so. In contrast, our models shows very different variability behaviors, with some being more variable than other, and also they show several fluctuations, but they show also an average accretion rate that is more or less steady. So, in this way, they seem in principle more suitable for long-term variability studies. So I have to mention one warning, that is that the models that we have considered so far still don't include magnetic fields, and therefore it is not possible to extract synchrotron emission-like curves, and therefore it is not possible to directly compare with the variability observed by the EHT or the variability predicted by other simulations. But this is something that we are currently working on. So I would therefore just like to conclude. The message that I would like you to transmit mainly is that the EHT observations already have a large constraint in power, so large that no model fits them at the moment. The most challenging aspect is probably variability, but at the same time we have seen that moving away from the typical theory that are used may give us different options to look at. So we have seen that a large-scale environment can drastically change the physics at horizon scale phenomenology. We have new models under development, and we hope that when the EHT improves also its observing technology with higher observing frequency, with adding more stations, and even when doing dynamical imaging, we'll be able to use these models to interpret the data. So thank you very much.
Thank you, Hector. Okay, I think we have time for a couple of questions. Milton.
A couple of questions, but thank you for the talk.
Thank you.
a little confused about what are the initial data for this simulation when you have large scale environment. What exactly, because essentially when we do Tori I, we just have the standard torus, but in here, I don't see it how you build. I mean,
What is the connection with the large scales? No?
yes.
So it comes in two ways. This doesn't work. So if you look at just at the transonic solution, well, the connection from the large scales comes because you can well, you can construct this transonic solution to match the observations that are well, that constrain the physics at much larger scales. For example, the Chandra observations can tell you more or less what is the accretion rate onto Sagittarius A star, even though they sample something that is at the order of 10 to the 5 gravitational radii. This is interesting because normally we well in most of the simulations that we have done so far, the accretion rate is something that you can vary more or less freely, and actually you can make it in a way that fits the observed flux that you have at some frequency. But using these models, this is no longer, you don't have so much freedom anymore, because the accretion rate, the mass accretion rate, is constrained by what you observe from the temperature of the medium, let's say, at much larger scales. And then you can so what you can get is just a prediction of how it would be at the frequency at which you want to test it. Interestingly, I mentioned it before that for these models we cannot directly well measure synchrotron radiation because we don't have magnetic fields. But what we did was to make a proxy of the Bremsstrahlung emission, because that one we can do. And interestingly, well, just using more or less reasonable data for Sagittarius A star, because we didn't want to fit anything, we found some emissivity, well, some X-ray luminosity that agreed quite well with what we have from Chandra, let's say. So this is one place where the large scale environment comes. The other part is by injecting these perturbations. So at the moment, the perturbations that we injected in the simulations are just white noise with some prescribed amplitude. But as knowledge on the structure of larger scale turbulence improves, we can adapt this spectrum and make it resemble something more similar to what we have in the real world. And so these are the two places in which the connection to larger scales appear.
Thank you. I think we don't have much time for more questions, maybe after the talk, because we have a second question, the second talk, sorry. But in the meantime, actually, I invite in the meantime, we are changing of the speaker. Maybe students wants to ask something to Hector. Students, everything is clear. Well, maybe Milton, you can ask more meantime.
So the other silly question that I have is, if you don't have magnetic fields, what is triggering the accretion?
Okay, right. So I mentioned before that for these models that simulate the accretion from the stellar winds, actually the magnetorotational instability is nearly suppressed. So what drives accretion in our models is the same well, the same thing that drives accretion on those other models, namely the fact that the matter has very low angular momentum. So well, the matter that the transonic solution has some rotation, but in general, this rotation is not that big to prevent matter to stop matter at a centrifugal barrier. So in general, matter can well reach the black hole almost directly without any angular momentum transport mechanism mediating. And if you include perturbations, that also can reduce the angular momentum in some places and make things directly fall into the black hole.
Yeah, but the thing is that I will assume that when for Sagittario A star and M87, the accretion disk has already relaxed. So
that's the usual assumption indeed. So that's the assumption that led to use this tori.
Exactly.
Exactly.
Yeah,
Yes.
yeah. So this is why.
And that's why people, well, up to now, used to think that the magnetorotational instability is the main mechanism that drives accretion.
Exactly.
Yes. But well, it turns out that the large scale simulations that considers the paths of all the stars don't show these kind of things forming. But I should say something. So to be completely honest, there are two groups that are in conflict about this. So the simulations from Chan Ressler and from Wu that I showed here are in favor of the approach that the matter has likely very low angular momentum and no disk is formed. But there is also another group led by, I forgot his name right now, but it's a group, Quartet, Elliot Quartet no, sorry, I'm mistaken. But there is another group in Heidelberg that maintains the contrary position, so that actually you have an accretion disk that is formed even at the larger scales. And yes, this is something very interesting to check indeed.
Let's change the microphone, please, Hector. Thank you very much. Okay, the second talk is Computational Insights into Multimessenger Astronomy by Inês Rainho, who is PhD student from València University. So please, Inês, the floor is yours.
Can you hear me?
Yes.
Okay. So, hello everyone. Thank you for the introduction. So, as Alejandro said, my name is Inês Rainho. I'm currently in my first year of the PhD in University of Valencia in Spain, and I am working in GRMHD, which stands for General Relativistic Magnetohydrodynamics Simulations, with Milton Rees, who gave a talk here on Monday. And today I want to talk to you about one of the projects that I'm working on. So, I think we can all agree that physics is an empirical science. We want to model our universe, so we are not mathematicians. And ideally, we want to have models that can accurately predict the fate of a given system. I recently read an article that said physicists are in the business of predicting the future more than fortune tellers and astrologers. So, to understand how accurate our models are, we need observations. And when we talk about astrophysical systems, there are multiple ways in which we can observe what is going on. We have, for example, neutrinos. Recently, we have gravitational waves, cosmic rays, and electromagnetic signals. When we can observe different types of these signals coming from a given system, we call this multi-messenger astronomy. And in 2017, with the detection of gravitational waves followed by a gamma ray burst from a binary neutron star, we opened a new window to a new type of multi-messenger astronomy, where we can detect, besides electromagnetic signals, we can detect also gravitational waves. To model sources of these types of, for multi-messenger astronomy, we need two things. We need systems that have strong gravitational fields so that we can actually measure the gravitational waves, and we need matter or magnetic fields so that we have an electromagnetic counterpart. So these types of systems can be either binary neutron stars, or we can have binary black holes surrounded by accretion disks. If we have a simple binary black hole in vacuum, we can detect gravitational waves, but we will not detect any electromagnetic signal. So I want to focus on the latter system. So when we have binary black holes surrounded by accretion disks, and there are two motivations. I have two main motivations to study these systems. First, they might explain these X-shaped patterns that we see in the universe, like these X-shaped galaxies. So how can they explain this? When we have binary black holes with spin, and the spin, if the spins are misaligned, they will precess, and when they merge, there will be a spin flip. This has been shown by Campanelli and others. And if we also have a magnetized disk, we will have jets, and the jets are aligned with the spins. So when there is the spin flip, we can have something like this. So these, there are, I think, around 11, a catalog of 11 of these galaxies, where we have a lobe that is brighter than the other. And we also see this in this observation, where we see this is black hole, and we see the jets in different directions. The other motivation is that this study from earlier this year has looked at unusual flaring activity in active galactic nuclei, and they have found 9 candidates to be electromagnetic counterparts for binary black holes that have been whose gravitational waves have been detected by LIGO. So there is some evidence that there might be some electromagnetic counterpart for binaries that we already detected. And another possibility to have these electromagnetic signals is that if there is some kind of asymmetry in the system, either the spins are misaligned or the mass ratio is different than 1, when the black holes merge and the gravitational waves carry linear momentum, if there is some kind of asymmetry, then by conservation of linear momentum, the final black hole will be kicked, and as it moves through the medium, it might accrete, and there might be a signal related to this. So I have a video illustrating both the precession, and you will see when they merge, when the black holes merge, the spin will flip, and then the video will be sped up to show the kick here. So now we want to study these systems. How can we understand these systems of binary black holes? So when we have 3 main phases. We have the inspiraling, the merger, and ring down. When the black holes are far away from each other, we can model their motion by post-Newtonian theory, and as they emit gravitational waves, they get closer to each other, and eventually they get so close that we can no longer do approximations, and we really need to solve GR. And for that, we use numerical relativity, which I will go into detail in a bit. After the merger, the black hole, the final black hole, emits gravitational waves that decay with a certain rate and have a certain frequency, and by that we can determine the properties of this black hole. And to study this phase, we use perturbation theory. So, okay, so numerical relativity. As I said, in the merger phase, we really need to solve GR. And if you know Einstein's equations, they look like this, but actually this is a very simple form. And if you put in everything in terms of the metric, you get something that is quite awful. And to solve these equations, we have analytical solutions, but these analytical solutions are only for when we have high degrees of symmetry, or when we work in asymptotic regimes, and thus we can make approximations and simplify everything. But in general, this is not the case, and so we need numerical methods to solve these equations. Generally, in GR, time and space are unified into a 4-dimensional manifold, so they are treated the same way. So, but as physicists, we want to see things evolving, and as I said, we want to make predictions. So it is useful to separate these two things. And a common way to do this is by separating time and space. And by doing that, we do that by foliating space-time into spatial slices. And we have some freedom in the way we do this. In particular, we can choose how much proper time passes between slices, which is determined by this alpha, which is the lapse function. And we can choose how the coordinates change from slice to slice, which is determined by the shift, the beta. If we do this, we can rewrite the Einstein's equations into different sets of equations, into evolution equations and constraint equations. So the constraint equations, we solve them to get initial data. And this is important because if we don't solve if these are not satisfied, we are not doing GR, but something else. And the evolution equations give us the evolution for these quantities, which is the spatial metric, which is essentially a metric that only lives in the slices, and the extrinsic curvature. The problem with these equations is that they are only weakly hyperbolic, which means that when you implement them numerically, your codes will crash. So there are a few reformulations, such as BSSN, which consists of doing some tricks, and you get something that is hyperbolic. But this is only for the gravitational part. I haven't talked about the matter. We also need to solve for the matter. And here, I think I will skip this a bit because Hector already gave an introduction for this. So the problem with matter is that when we have matter, we can have chocks, and this makes everything much more complex. And we cannot do, for instance, convergence tests for these cases. Well, okay. So as I said, I want to model binary black holes with accretion disks. So to start with, we need to build our initial data. And to build our initial data, we start with a Kerr black hole, a single Kerr black hole, and we find an analytical solution, which is stationary, for a disk which we consider that as a power law rotation dependence. So the angular velocity has this dependence where eta is a coefficient, lambda is the ratio between the specific angular momentum and the angular velocity, and q is another coefficient. And the solution for the disk is uniquely determined by this coefficient in the power law expression. The innermost radius of the disk, so this, and the specific angular momentum at that distance. After we have this solution, we substitute the single Kerr black hole by a binary. So here actually we are not solving the constraints to get the initial data, and in that sense it is not self-consistent, but we place the innermost radius of the disk well outside of the orbital radius of the black holes, so that the approximation is valid. And after this, we seed a poloidal magnetic field. And I have a video of this evolution. Here we have so these colors are the rest mass density. The green lines are the magnetic field inside the torus. We have the two black holes there. Well, I don't think you can see it, but it will zoom in a bit. And we start the simulation. You will see that the magnetic field lines get twisted. And eventually you will see these white lines that are the field lines that are emerging from the black holes. In these simulations, we had spins, misaligned spins of 0.26, and you will see that the jets coming from both black holes are aligned with the spins of each black hole. So here we zoom in, and you can see that they are aligned. But the issue here is that the spins are so low that what dominates is not the direction of the spin, but the field from the disk. So if we want to see something, this tells us that we have to go to I spins. And this is what I am currently doing. I am running simulations like this, but with higher spins. And we want to see these. So we want to see if there is, if we have a spin flip and a jet flip as a consequence of that. There is some problems that arise from having a higher spin, in particular if we have misaligned spins, because if we have spins, then the horizons are not spherical, but something like an ellipsoid. And if they are misaligned, we have something like in different directions. And in these simulations, we use multiple levels, which we call refinement levels. And as we get more to the smallest levels, the resolution is higher. But the problem is that if we have misaligned spins and the horizons look different, then we have to fix that problem. So I think I did this very quickly. So the main point of this talk is trying to convince you that binary black holes can be sources for multi-messenger astronomy. And they can explain these X-shaped galaxies, but also maybe we can do multi-messenger astronomy and not necessarily to explain this, but we already have 9 candidates for binary black holes that we have detected. So yes, and then there are other things that we want to do after we have these results, because I'm still running the simulation, so I still don't have any results. So one thing that we want to do is do calculations with radiative transfer. In particular, we want to answer the question, can we distinguish an image from a single black hole or a binary? And then we can move on to more realistic simulations. For instance, we are only considering massless disks. When we move on to massive disks, we really need to solve the constraints because the metric is no longer curl-like. We would ideally like to consider realistic cooling effects. This will change the accretion rate and get self-consistent initial data. I think that's it.
Thank you very much. Okay, I think we have enough time for questions. Ivan?
Thank you, very nice talk. What's the matter profile that you use for the accretion system? So the magnetic field is at torus, but the matter profile, what's the?
So there is no matter here.
Oh, no matter.
So yes, it's only B field. For now we are considering only massless disks.
I see. So
But you can have a profile of density and pressure, even if you consider that the disk is non-gravitational.
I mean, my question. Yeah, because I wanted to know what kind of profiles of matter you would need in order to reproduce these X-shaped patterns, like initially, or what kind of spins configurations you would need in the binary.
Okay, so I don't know if that is the question, but the disks are a torus, and we get the solution for the disks. We use the same initial data as Ferris, and for the spins to get the spin flips, we have okay, so for the spin flips we really need the misaligned spins, and right now we are running simulations like with the spins like this and 0.9. So we because we also want to maximize the kick velocity, and there are some studies that have shown that at least in vacuum we can have kick velocities of 2000 kilometers per second with I spins. So we want to maximize that, but for the spin we just need for the spin flip we just need misaligned spins, because if they are aligned there will be no precession.
I think I would like to rephrase the question maybe from Ivan. The question is, for example, for me is, what is the equation of state are you using for the torus, for example? Or there is ideal gas equation of state?
it's a gamma law
Sí.
equation. Like,
Okay, okay.
That we start with actually why I was asking Hector about this is that at the beginning we can put any disk we want or any distribution of the disk we want. The thing is that what we expect is at some point that this is going to get relaxed. So we expect that we will have, because we have MRI, once again, the thing with Hector, then that's going to trigger the accretion disk, and then the shape that we have here of the disk that is essentially a torus is going to change, because we don't expect that this kind of disk we will have something that is more relaxed. So we will have, I mean, I don't know, a lot of turbulence like that they wouldn't agree that the disk. So, I mean, we don't expect any, I mean, this is a really simplified model. When we reach the equilibrium state, when the disk is relaxed, then that's what we are going to use as initial data. After that point where we will see how the jets form in the spiral, and then after merger we will see the spin state to see what kind of change. But once again, you have to start with something, and then we start with this simplified model, then we reach the state where it's relaxed. And then the point we can somehow simulate this.
Okay, thank you. Thank you.
Yeah. Okay. Sorry, Hector.
Thank you. So there is a paper from this year, I think. I don't remember the first author, but is this someone from the group of Sasha Shekovsky with the hammer code, which tried to explain these X-shaped radio galaxies in a alternative way. They claim that this X shape could be because one of the because basically there is the jet that is launched from a single black hole is trying to fight against the resistance of the medium, and then this causes it to change directions until it aligns with the spin of the black hole. And I was wondering, besides observations of very long wavelength gravitational waves from these systems, is there any other observable, especially an electromagnetic observable that one can use to distinguish between binary black holes and single black holes, something like distinctive?
Besides the gravitational waves.
Besides the gravitational waves, so is there something that we can look in the electromagnetic spectrum and say that is a sign of binary black holes?
I actually don't know, but I like the gravitational waves would be a different. You couldn't see the difference by detecting gravitational waves. I don't think for an electromagnetic signature, I don't know.
I see. So we need gravitational waves.
Yes.
Thank you.
Think so.
Wait. Let's use the micro, please.
Yeah, also, as Inês was saying, also, if you have radiation transfer, this is the stuff that we want to do with you. Then the question is if we can distinguish using just photons, if there is a difference between a binary and a single black hole. And this is something that we are working, who will be working with Alejandro. But right now, we don't know. I haven't seen any simulation that is actually showing that we can have a jet. I know that paper that you mentioned, and yeah, that's another possibility, but we don't know.
Okay, thank you. We have a comment on in the chat. Any kind of periodic phenomenon? Well, maybe trying to say that to measure some light curve, maybe. But this is exactly what we want to do. No?
Exactly. So we don't know yet.
Yeah, so if you have this simulation that it's a binary black hole merger, what is the mass ratio that you need in order to have that yet? And because if you have a mass ratio like 0.1 or slow mass ratio, I believe that you are going to have all in the black hole, not launching anything.
Can you repeat? Well,
What is the mass ratio that you need in order to launch a jet?
So the mass ratio that we can have mass ratio equal to 1 to launch a jet. We want a mass ratio different than 1 to see the final black hole being kicked. Because to do, we don't need to have that, but that's a possibility. If we have misaligned spins, we will have a kick. We need some kind of asymmetry so that the gravitational waves will remove linear momentum, and if they were the same mass, then everything would be symmetric, and the final black hole being still would conserve linear momentum. But if there is if one is bigger than the other, then when they merge, there will be a kick.
Okay.
No?
Okay, thank you. Well, pass.
So essentially, as I think Alejandro showed us at some point this week, the phenomenon or the mechanism to get the jets is just the spin of the black hole. So if you have a curved black hole with accretion disk, you will get a jet. That's essentially what Inês is trying to say. So it doesn't matter of the mass ratio. You always, if you have spin, then you will have a jet.
And magnetic.
Yes, so and magnetic fields, of course. And then the thing is that we want to see, once you have the jets that are pointing along the direction of the spins, in here we have spins that are pointing on the or are on the plane XY. So we will have jets on that plane, and the idea is that during the merger, you will see the spin flip. It's going to be pointing along the Z direction where the total angular momentum of the system is taking place. So that is going to change the direction of the spin. You will have individual spin at the beginning and then a single spin, black jet pointing toward another direction. And then with radiation transfer, we expect that we will see some X-shaped form, but the mass ratio doesn't play any role here, as long as you have spin.
Okay, thank you very much for the comment. I think we have another comment in the chat. Professor Deborah says there are periodic light curves in the blazars explained by the presence of the binary black holes. Do you like to comment something, Inês?
I don't know about this.
Okay, yeah, it's basically electromagnetic radiation from observation. So they are looking like periodic variation into the light curve at some specific frequency. And they say that this is the evidence to have a binary black hole. Actually, this is something that you want to do, right? So she says, professor says, example, OJ287, both in radio and optical light. So yes, it's basically, I think you can do this after post-processing, no? Doing radiation.
Okay.
Even in that case, well, I mean, it is not that I want to contradict this, but so just to have the complete picture, even in this case, I think that the periodic light curves from lasers could also, well, have been also proposed to be attributable to precessing disks. So a disk could precess due to the length theory precession, and I think there is even a paper by Silke Britzen on OJ287 where well, they maintain that this could be due to a precessing jet. And yes, so
Thank you, Hector, for your comment. I think, yes. So basically there is, yes, two models, no? One, the binary, and then the other, the tilted disk, right? But yes, actually this is exactly, you have to solve this question, no? From your simulations. Okay, well, let's thanks again to Inês for this very nice talk. And we will close here the call. Thank you very much.